A wave of dangerous heat just rolled across the American West this weekend, and it broke temperature records that had stood since before airplanes existed. But researchers tracking this event say the number on the thermometer isn't actually the part that should worry you most. It's what that heat landed on top of. Because this particular heat wave didn't arrive on ordinary ground. It arrived on top of some of the driest soil, the lowest reservoirs, and the thinnest mountain snowpack this country has measured in over a century. And scientists studying the interaction between the two say that combination behaves nothing like a normal summer scorcher. Right now, we're going to break down exactly how hot this weekend got, what's sitting underneath that heat that's making it so much more dangerous, and why researchers say the real story here isn't the heat wave itself, but the ground it's landing on. Let's start with the numbers, because they're genuinely staggering on their own. Over the weekend, extreme heat warnings blanketed huge sections of Arizona, California, Nevada, and Utah, with temperatures running somewhere between 7 and 12 degrees Fahrenheit above what's normal for early August. Reno hit 103 degrees on Friday, shattering a daily record that had stood since 1990 at a weather station that's been keeping continuous records since 1888. Salt Lake City matched that same 103-degree mark, breaking a record for that specific date that had been tied 3 separate times going back to 1994 at a station with records stretching all the way back to 1874. When a single weekend breaks marks that old, in 2 different cities hundreds of miles apart, that's not noise in the data, that's a signal. And once again, the overnight numbers are the part meteorologists keep flagging as the real danger. Across the Mojave Desert, lows only dropped into the 80s, and in some spots stayed as high as the mid-90s even after midnight. In the broader basin and range country of western Nevada, overnight lows sat in the upper 60s to mid-70s, which sounds mild until you remember that's supposed to be the several hours a day when both the human body and the surrounding landscape get a chance to recover before the next day's heat begins building right back up on top of it. Here's where the story stops being just another hot weekend, though, and starts becoming the thing scientists are genuinely watching closely. This heat wave didn't fall out of a clear sky onto normal terrain. It fell onto a landscape already primed by one of the driest years this country has measured in more than a century. Go back to the first 3 months of this year, and the numbers are almost hard to believe. Nationally averaged precipitation across the first quarter came in at under 5 inches, the lowest total ever recorded for a January through March stretch in over 130 high years of tracking, edging out the previous record, low set back in 1910 during the era of the Dust Bowl. That extraordinary dryness, combined with spring temperatures running 5 to 10 degrees above normal across huge sections of the country, pushed more than 80% of the continental United States into some level of abnormal dryness or outright drought by the time spring wrapped up. And as of the first week of this month, drought was still gripping over 40% of the entire country, with conditions actively worsening across the Pacific Northwest, even as some relief crept into pockets of the Central Plains and Upper Midwest. Understanding why that matters requires understanding something most people never think about, which is how deeply connected the ground beneath a heat wave actually is to the heat wave itself. Picture 2 identical patches of Earth sitting side by side under the exact same blazing sun. One patch has normal soil moisture. The other is bone dry, the way huge stretches of the West are sitting right now. In the moist patch, a meaningful share of the sun's incoming energy gets absorbed doing something called evaporation, essentially converting water in the soil into vapor, a process that consumes enormous amounts of energy without raising the air temperature much at all. It's the same principle behind why sweating cools your skin, but in the dry patch, there's no water left to evaporate. All of that same solar energy has nowhere else to go, so instead of getting soaked up by evaporation, it goes almost entirely into heating the ground and the air sitting directly above it. Multiply that difference across millions of acres of already parched western landscape, and you get a heat wave that runs measurably hotter and holds on to that heat measurably longer than the exact same weather pattern would have produced over normal moist ground. Dry soil doesn't just sit there passively while a heat wave passes through. It actively makes the heat wave worse. If you're finding this breakdown useful, go ahead and hit that like button. It genuinely helps this kind of climate coverage reach more people who need to actually understand it. A feedback loop is exactly why researchers were already sounding alarms months before this particular heat wave ever arrived. Back in the spring, climate scientists studying the West's rapidly vanishing mountain snowpack warned that even though soil moisture looked reasonably close to average at that point, it would almost certainly end up significantly below average by the time summer hit its peak, once low snowpack finished melting out early and stopped feeding streams and soil through the hottest months. That's precisely the mechanism now playing out in real time underneath this weekend's record heat. And it's compounding with consequences well beyond just how hot the air feels. Reduced humidity accompanying this heat wave has pushed relative humidity down into the single digits across parts of Nevada during peak afternoon hours, drying out vegetation to the point where the U.S. Forest Service issued enhanced wildfire risk warnings across most of Southern California, while red flag warnings covered wide stretches of Montana, where fires were already actively burning even before this latest round of heat arrived. The water system underneath all of this tells the same story from a different angle. Back in March, the water district responsible for supplying 19 million people across Southern California issued its first formal conservation notice of the year, a direct response to a winter that simply never delivered the recharge those reservoirs depend on. Multiply that single example across the broader Colorado River Basin and the Mountain West generally, and you're looking at a water system trying to support the exact same population and agricultural demand it always has, on a meaningfully smaller water budget than it was designed, around right as heat demand for that water peaks. Even earlier warning signs showed up in agricultural regions far from the desert Southwest. A heat wave that swept the northern and central plains back in July stripped soil moisture out of the ground so quickly across parts of the Dakotas, Nebraska, and Kansas that drought monitors flagged rapidly expanding dryness there within days, a preview of the exact same feedback loop now playing out on a larger scale across the West. None of these threads exist independently of each other, and that interconnection is precisely the pattern scientists keep returning to. A drought-driven feedback loop makes heat waves hotter and longer. That extra heat further dries out vegetation, expanding wildfire risk into areas that wouldn't normally see it this severely. Smoke from those fires then combines with the heat itself to degrade air quality across huge population centers, adding a respiratory health risk stacked directly on top of a heat health risk. And underneath all of it, water managers are stretching a shrinking supply across the same demand, with less of a cushion than they've had in generations. Each piece individually is manageable. Layered together the way they are this year, they compound. And that compounding is exactly the dynamic that's much harder to model, much harder to forecast, and much harder to communicate to the public than a single number on a thermometer ever could be. Subscribing means you won't miss the next update the moment new information comes in on how this pattern develops through the rest of the season. Zoom out to the bigger picture, and there's a genuinely important, complicating wrinkle scientists are watching unfold. The record dryness driving this whole chain reaction traces back largely to a La Niña pattern that dominated the first few months of the year, but forecasters have been tracking growing signs that conditions are now shifting toward an El Niño setup as the year progresses, a pattern shift that historically tends to bring more moisture toward the southern half of the country, especially heading into fall and winter. That's genuinely good news if it plays out, but it's also exactly why researchers are urging caution against assuming rain later. This year automatically undoes the damage already sitting in the ground right now. Soil moisture deficits and snowpack shortfalls built up over an entire winter and spring don't simply reset the moment a few storms roll through. They take sustained, well-distributed deprecipitation over months to genuinely recover, and a couple of dramatic rain events. Instead, often just run off parched, hardened ground rather than soaking in the way the system actually needs. There's also historical context worth holding on to here, because this isn't the first time this exact chain of events has played out, just usually not quite this early or this severe. 2 years ago, in what still stands as the deadliest heat year on record across the Southwest, heat-related illness was linked to more than 660 deaths in the Phoenix area alone, and roughly 340 in the Las Vegas area. Numbers that climbed specifically because prolonged triple-digit stretches gave neither the human body nor the surrounding landscape any real chance to recover. Researchers studying this year's setup say the underlying ingredients, a heat dome sitting over already parched ground, are disturbingly similar, arriving even earlier in the drought cycle than they did back then. So what actually comes next, according to the researchers, watching all of this unfold in real time? Some genuine relief is on the way in the immediate term, with monsoon moisture expected to push into the Four Corners region within the next several days, which should knock temperatures down from this weekend's extremes. But that short-term relief and the longer underlying deficit are two completely different timescales, and scientists are explicit that one doesn't meaningfully fix the other. The soil, the snowpack, and the reservoirs sitting underneath this heat wave were shaped by an entire winter and spring of record dryness, and they'll need a comparably sustained stretch of normal or above normal precipitation to genuinely recover, not a handful of monsoon storms squeezed into a few weeks of August. If you're anywhere across the region dealing with this heat directly, the guidance from public health officials remains straightforward and worth repeating regardless of how many times you've heard it before. Limit outdoor exertion during peak afternoon hours, especially with humidity this low and air quality this degraded in wildfire-adjacent areas. Check on elderly neighbors and anyone without reliable air conditioning. since overnight lows this high mean their bodies are getting essentially no recovery window at all. And treat any wildfire smoke advisory in your area as seriously as the heat warning sitting right alongside it. Because this year, the two threats are arriving together far more often than they used to. The temperature records set this weekend will eventually fall out of the headlines, replaced by whatever the next hot day happens to produce. But the ground underneath this heatwave isn't resetting along with the news cycle. It's carrying forward every deficit built up since January into whatever comes next this season, and scientists studying that ground say it's no longer really a story about how hot the air got this weekend. It's a story about how little water was left underneath it to fight back.